This lesson is on rational functions. Now, we've discussed rational functions previously in Module 1, and you know that rational functions are functions that are written as a ratio. So I could give you something like x squared plus 7 over x minus 3, so written as a ratio. It's just a polynomial divided by a polynomial. We know that rational functions typically have asymptotes. So we might get a graph that looks something like this. This, by the way, is not the graph of this particular function. But so let's get on to our definition. So a function that can be written in the form f of x equals p of x divided by d of x, where p of x and d of x are both polynomial functions. Remember, a polynomial function is one that's written in the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 all the way till we get to a sub 0. So we've got some degree, whatever our leading degree of our polynomial is, and n here determines the degree. So if I had like 7x to the 43rd power, then that would be a polynomial to the 43rd power. We know that the leading coefficients have to be real numbers. So a is an element of the real numbers, is how we write that. And we know that n has to be an element of the integers, and it must be greater than 0. So whatever that leading degree is, whatever that power is, it's an integer and it's greater than 0. So again, rational function is a function written in the form f of x equals p of x divided by d of x, where p of x and d of x are both polynomial functions. We also know that d of x is not 0 because we can't divide by 0. And then that's the definition of what we call a rational function. Okay. Remember, p of x is my numerator. That's the polynomial in the numerator. And d of x is the polynomial that's in the denominator. Okay, the domain of f, or so the domain of the rational function, is the set of all real numbers x, as long as d of x, the denominator, does not equal 0. That's my only restriction, is that the denominator can't be 0. I can't divide by 0. Okay, so in our examples below, we're supposed to determine the domain of the following functions, and then we're going to write our answers in interval notation. So the first one is f of x equals x to the 5th minus 3x plus 2 divided by x. That's a rational function. I have a 5th degree polynomial in the numerator and a 1st degree polynomial in the denominator. Now remember, the only restrictions on my domain is that the denominator cannot equal 0. Okay, so in this case, I'm going to look at the denominator, it's x, and I know that x cannot be 0. That's the only restriction on the domain. So that means if I want to look at a number line, x can be anything, but x can't be 0. So when I write my answer in interval notation, the domain is negative infinity to 0, union 0 to infinity. And that would be my answer. Super easy for that one. Let's move on to something a little more complicated. So for the next problem, f of x equals 3x cubed minus 31x minus 18 divided by x cubed plus 3x squared minus x minus 3. So I have a 3rd degree polynomial in the numerator, 3rd degree, and a 3rd degree polynomial in the denominator. Now again, the only restriction I have on the domain is that whatever the denominator is it can't equal 0. So x cubed plus 3x squared minus x minus 3 cannot equal 0 because I can't divide by 0. So first thing I need to do is I need to factor the denominator to figure out which values of x would cause it to equal 0, and I can exclude those values of x from the domain. So from the first two terms, I'll factor out an x squared, leaves me with x plus 3. And then from the next two terms, I'll factor out a negative 1, so x plus 3. Okay, so now that each of these terms has an x plus 3, I can factor that out. So x plus 3 times x squared minus 1. So, and we're almost done factoring, but not quite here. So x plus 3. And then x squared minus 1 factors to x minus 1 times x plus 1. Now it's fully factored, which means I can set each of the factors equal to 0 and solve. So x plus 3 cannot equal 0, x minus 1 cannot equal 0, and x plus 1 cannot equal 0. Those are my restrictions, which means x does not equal negative 3. I'm going to subtract 3 from both sides. X does not equal 1. I added 1 to both sides. Subtract 1 from both sides here, so that x does not equal negative 1. So these are my restrictions on the domain. So when I write my domain, again, if you want to use a number line, you can. X cannot be negative 3. X cannot be negative 1, and it cannot be positive 1. But it can be any other value. So the domain is negative infinity to negative 3 union negative 3 to negative 1 union negative 1 to 1 union 1 to infinity. And that is your final answer. Okay, so we are going to learn a lot about rational functions today, okay? There's a lot that we can tell just by looking at the numerator and the denominator. We're also going to look at the degrees of the polynomial, and that'll give us additional information about our rational functions. So lots of detailed work today as we learn more about rational functions. Okay, so the first thing we're going to look for in our rational function are wholes. And so I've got this rational function f of x, it's equal to p of x over d of x. We're told it's a rational function, which means it's a polynomial divided by a polynomial. And then I'm told that if c, so some number c, is a root of both p and d. Now remember, p is the numerator and d is the denominator. Okay, so I've got this number, it's a root of both. Then that means that x minus c is a factor of both the numerator and the denominator. Now, we've done this previously when we worked on polynomials. Remember, if I told you that a root was maybe 7, then we knew that the factor was x minus 7. So same idea here. I've got this root c, which means that x minus c is a factor. Okay, and in this case, it's a factor in both the numerator and in the denominator. That's what's important about wholes. It has to be in both the numerator and in the denominator. And if that's the case, then there is a hole in the graph of f where that common factor occurs. Okay, and the hole will occur at the point whatever c is, whatever the value of c is, and then f sub s of c after f has been simplified. Now, this f sub s, we're going to use this notation. So s sub s of x is going to represent the polynomial after we have removed the common factors, after we've eliminated the common factors. So that's the polynomial with the common factors eliminated. Okay, so in our example, we're supposed to determine the point in which the graph of f of x has a hole. And we're given this polynomial 3x cubed minus 31x minus 18 divided by x cubed plus 3x squared minus x minus 3. So a third degree polynomial divided by a third degree polynomial. First thing we've done is we've factored it, which is important because I can't do much without factoring it. And then I'm going to look for those common factors. And I can see I have a common factor of x plus 1 in the numerator and x plus 1 in the denominator. Okay, so that means that I have a hole. Well, my hole is at x equals negative 1. Remember, if the factor is x plus 1, then that means the root is negative 1. You have to change the sign. So I have a hole at x equals negative 1. So the first thing I need to do then is I need to find the simplified version of this function. So in this case, the simplified version without those common factors, go ahead and eliminate those common factors, is 3 times x minus 3 times x plus 2 divided by x minus 1 times x plus 3. And then to find the actual location or the y value for that hole, I know where the x coordinate is, but I need the y coordinate. I'm going to substitute in for x where the hole is at negative 1. So the simplified version of negative 1 would be 3 times negative 1 minus 3, negative 1 plus 2 divided by negative 1 minus 1 times negative 1 plus 3. So this equals 3 times negative 4 times 1 divided by negative 2 times 2, which equals negative 12 over negative 4, which of course is 3. So that means my hole is at negative 1 3. Okay. All right, so now I've got that information. I know where my hole is. Next, I want to find my vertical asymptotes, okay? So the vertical asymptotes in the holes, and for that matter, are where the denominator is equal to 0. And that is going to correspond to either a vertical asymptote, that's your blank here, or a hole in the graph. Now, we're always going to find our holes first. Once we find our holes, then we're going to create that simplified version without those common factors. And that means everything else in the denominator is going to lead me to my vertical asymptotes. So let's let f simplified of x, so you see my S here, that means simplified without the common factors, is equal to P of x over D of x, a polynomial divided by a polynomial. It's a rational function in simplified form, which of course, like we just said, just means that all of the common factors of the numerator and the denominator have been eliminated. Then if D of B equals 0, now D of B just means the denominator. So if the denominator equals 0, then x equals b is going to be a vertical asymptote. Okay, so whatever those values are that cause the denominator to then go to 0, and I know I can't divide by 0, that's where the graph is undefined, is a vertical asymptote. Okay, and then there's a couple of things that play out here that are similar to what we've talked about before. When the multiplicity of b, whatever that value is that makes the denominator go to 0, when that multiplicity is odd, that's your blank, when the multiplicity is odd, then the graph is going to approach positive infinity on one side of x equals b and negative infinity on the other side of x equals b. So remember, b is a vertical asymptote. So here's my vertical asymptote at b, okay? And let's assume that the multiplicity is odd. So maybe I have x minus b could be to the first degree, or x minus b to the third degree in the denominator, okay? So odd multiplicities. Then that means it's going to approach positive infinity on one side and negative infinity on the other side. Now, we've done something similar with this when we talked about x-intercepts with polynomials. And we knew that when we found the x-intercept, if the multiplicity was odd, then the ends went in opposite directions. It crossed the x-axis with ends going in opposite directions. Same idea here, but now we're dealing with an asymptote. So it could be that to the left of the asymptote goes to positive infinity, to the right of the asymptote goes to negative infinity. Or, still odd, still have a vertical asymptote at b, but maybe on the left side of the asymptote, I go to negative infinity, and on the right side, I go to positive infinity. So the fact that the multiplicity is odd just tells me that the ends go in opposite directions. That's what's important, okay? Now, the other scenario, of course, is that the multiplicity of b, if it's not odd, then it must be even. Okay, and then if that's the case, then the graph of x or graph of f will approach positive or negative infinity on both sides of the asymptote. So similarly, when we did x-intercepts, if it was even, it would touch the x-axis and turn back. The ends would go in the same direction. We had the same thing here. If the multiplicity is even, then if it goes to positive infinity on the left side of the asymptote, it'll also go to positive infinity on the right side of the asymptote. Or it may be that around b, it goes to negative infinity on the left side, and if it's even, it goes to negative infinity on the right side. So cases of even would be something like x minus b squared, or x minus b to the fourth. These are even multiplicities, okay? And so the behavior, they would both go in the same direction when it's even. Opposite directions for odd, same direction for even. Okay, so for our next example, we are to determine the simplified form of f of x equals 3x cubed minus 31x minus 18 divided by x cubed plus 3x squared minus x minus 3, and then I've given it to you in factored form. And then we're going to find the vertical asymptotes. So first thing we always want to look for is we want to look for the holes, okay? And this is the same problem we worked with earlier up above on your paper, and we know there's a hole at x equals -1. Once you find that hole, we're going to eliminate those common factors and write the simplified version. So once we find the hole, we write the simplified version, and that's what we deal with for the rest of the problem. That's all we refer back to is the simplified version. So my simplified version is 3 times x minus 3 times x plus 2 divided by x minus 1 times x plus 3. So simplified version with the common factors eliminated. And then I want to find the vertical asymptotes. Well, again, the vertical asymptotes are where the denominator is equal to 0. So the vertical asymptotes is where the denominator equals 0. Okay, so that means I'm looking for where x minus 1 times x plus 3 is equal to 0. So since it's already factored, I can set each of my factors equal to 0. And so that means that x equal 1 will give me a 0 value, and x equals negative 3. So these are my vertical asymptotes. I have a vertical asymptote at x equals 1 and a vertical asymptote at x equals negative 3. Okay, and remember, you write your asymptotes, your vertical asymptotes, always as x equals. And then from here, I want to determine what the behavior is on either side of the asymptote. So let's look at x equals 1 first. Okay, so I have this graph. Here's 1, there's my vertical asymptote at x equals 1. Okay, so to test the behavior, all I really want to know, I know it goes to infinity on both sides of the asymptote. It either goes to positive infinity or it goes to negative infinity. So the only thing I'm really interested in here is the sign. Is it positive or is it negative? So I'm going to choose some value that's smaller than 1, something to the left of 1. I could use 0, I could use 1/2. Something close to 1, but I don't want to use negative 10, but something close to 1, but just to the left of it. So 0 is obviously going to be the easiest value to choose. Okay, so if x is equal to 0, I want to know what happens. What's the sign? Okay, well, back into my original function, into its simplified form, I'm going to look at the simplified version, f simplified of 0. So that means I'll have 3 times 0 minus 3 is negative. All I care about is the sign. 0 plus 2 is positive. Okay, that'll be divided by 0 minus 1, which is negative, 0 plus 3, which is positive. So that means in the numerator, it'll be 3, which is of course positive, times a negative number times a positive number. That'll give me a negative number in the numerator, divided by a negative number times a positive number is a negative number. So a negative divided by a negative, of course, is a positive. So what that means is on the left side of x equals 1, it's going to go to positive infinity. Okay, and I can go ahead and add that to my picture here. This is going to go to the positive infinity. Now, because the multiplicity is 1, and where I get that from is I look at my factored form and I can tell this is to the first degree and this is to the first degree. Well, because the multiplicity is 1, then that means the ends are going to go in opposite directions around the asymptote. So if it goes to positive infinity on the left side of the asymptote, it has to go to negative infinity on the right side of the asymptote. Okay, so I know the behavior now around that vertical asymptote. Next, I'm going to look at my vertical asymptote at x equals negative 3. So I'll just add it here to the same graph. There's my asymptote. So x equals negative 3, and then just do a test point around negative 3. So I'm going to choose something to the left of negative 3. I'll probably do x equals negative 4. That's an easy value. And again, all I'm looking for is the sign. So I put that back into the simplified equation. Okay, and so that means the numerator will be 3 times, so negative 4 minus 3 will be a negative number. Negative 4 plus 2 is a negative number, divided by negative 4 in the denominator will be a negative number. Negative 4 plus 3 is a negative number. Okay, so the numerator will be 3, which is positive, times a negative, that'll be positive in the numerator, divided by a negative times a negative will be positive in the denominator. So my answer is positive infinity. So at negative 4, or for values less than negative 3, I'm going to head towards positive infinity. And again, because the multiplicity of this is odd, then the ends are going to go in opposite directions. So that means for values on the right side of negative 3, it's going to go to negative infinity. So now I know what the behavior is of this graph. And if I were to connect this graph in the middle, it probably looks something like this. And in fact, as we go on down the road, I'll be able to find the x-intercept and figure out exactly where it crosses. I'll be able to find the y-intercept and have a much more precise graph. At this point, I don't know where the horizontal asymptotes are, And so I'll get more and more information and be able to do a better job graphing this, but it likely looks something like this. Okay, so next we want to be able to find those x-intercepts. So we've basically, so far we know how to find holes, we know how to find vertical asymptotes, and then next we're going to find x-intercepts. So the x-intercepts of a rational function, that's your first blank here, x-intercepts of a rational function can be found where the numerator is equal to 0. Now remember, vertical asymptotes are where the denominator is equal to 0. So keep those straight. So where the numerator equals 0, then that is where the x-intercepts are, as long as that value is in the domain. Now, as long as we find our holes first, and we go ahead and eliminate those common factors, then we don't have to worry about domain restrictions. We will have already covered that. Okay, so let f of x equal p of x or over d of x. Again, p of x is a polynomial divided by d of x, which is also a polynomial. And we're told that if a, some number, is a root of p of x, remember p of x is the numerator, okay, then because it's a root, we know, of course, that x minus a is a factor. Then by the factor theorem, we know that p of a is equal to 0. Okay, and if a is a root of p of x and not a root of d of x, and it won't be because we will have already eliminated those common factors, then a0 is going to be an x-intercept of f. Okay. And this is very similar this is the same idea as what we picked up in our study of polynomials. When we look at the factors, if we know that a value is a root or a 0, okay, then we know that that number is an x-intercept, which means that that point, comma 0 will be an x-intercept. Okay, so the graph passes through the x-axis then at the point a0. It's going to pass through when the multiplicity of a is odd, okay? And it's going to touch and turn back when the multiplicity of a is even. This is what we learned with polynomials. So if I'm looking at odd multiplicities, so let's assume that we have x equals 2, and that's a root, okay? So if 2 is a root, then we know that x minus 2 is a factor. Okay, which tells us that we have the point 2, 0, which of course is an x-intercept, okay? If the multiplicity of 2 is odd, so x minus 2 is to the first degree, then I know I have an x-intercept at 2. And because it's an odd multiplicity, it's going to cross through with ends going in opposite directions. Now, I could also have an odd multiplicity of 3. So something like x minus 2 cubed would be an odd multiplicity. 3, of course, is odd. And in that case, then it would pass through similar to a cubic, something like this, okay? Now, it doesn't have to head that direction. It could also come down. It could look something like this, okay? But I get that bend, and the higher the multiplicity, the more it flattens out around the curve. So x minus 2 to the 5th would be even flatter around the root, okay? So those are odd multiplicities. Ends go in opposite directions. Now, in the case of even multiplicities, so let's see, I'm looking for an even multiplicity. So maybe I have something like x minus 2 squared. Then I know this is going to behave like a quadratic. So again, the root is 2. And in this case, the ends are going to go in in the same direction because it's even. So it's going to come down, it's going to touch the x-axis, and then it's going to turn and bounce back, okay? Something like x minus 2 to the 4th. So again, an even multiplicity. Maybe we'll make this one go down this time, okay? And this one's going to look different because it's going to flatten out around the root. Okay, so as the multiplicity increases, it gets flatter around the root. Smaller multiplicities are like that would behave more like a quadratic around the root. So that really should be a review from polynomials. That's really the same discussion we had there. Odd multiplicities go in opposite directions. Even multiplicities are going to go in the same direction. Okay, so we're supposed to determine the x-intercepts of f of x. This is the same function we're looking at. Now remember, before you do your x-intercepts, the first thing you always want to do is eliminate any common factors, and we've got that common factor at x plus 1 in the numerator and x plus 1 in the denominator. We know that indicates where the whole is. If you don't eliminate those, you're going to end up telling me that that's an x-intercept, and that's going to be wrong. So always take the common factors out first. That's super important. And then that'll give us that simplified version of the function, which is 3 times x minus 3 times x plus 2 divided by x minus 1 times x plus 3. Okay, and then so now when I look for my x-intercepts, I know that that's where the numerator is equal to 0. So 3 times x minus 3 times x plus 2 equals 0. So set each of the factors equal to 0. So x minus 3 equals 0 and x plus 2 equals 0. So that means x equals 3 and x equals negative 2. Now remember, I'm looking for x-intercepts here. Okay, so you don't leave it like this. My x-intercepts are at 3, 0, and negative 2, 0, and that would be your final answer. We look at only the factors of the numerator that are not also in the denominator. So eliminate those common factors first to get rid of the whole, and then move forward from there. Okay, so now we're going to put all of this together. We're going to determine the domain, find any x-intercepts, vertical asymptotes, and holes for the graph of each irrational function. So we're going to do, there's a particular order this makes more sense in than any other. So you always want to look for the holes first. That's always the first thing you want to find, because then once you find those holes, then we're going to create the simplified version of the function. Once you've got the simplified version of the function, that's what you use to find everything else. And then you'll never get these wrong, okay? So always find your holes first. After you find your holes, then we're going to look for the vertical asymptotes. Vertical asymptotes, remember, are where the denominator is equal to 0. After you find the holes and the vertical asymptotes, remember, those are the two areas where the graph does not exist. So at that point, you know which values are not a part of the domain. So the next thing that makes the most sense to find then, of course, is the domain, knowing that the domain will exclude the vertical asymptotes and exclude any holes. And then finally, the last thing you'll want to find is your x-intercepts. So that's the order that we're going to work in. So just realize that sometimes when you're given a homework problem or a test problem, it's not going to be laid out that way for you, but you're going to want to make sure you always find the holes first, and then from there the vertical asymptotes. And then after that, it's kind of up to you. I would definitely do domain next. And then, you can decide, do you want to find x-intercepts? We're eventually going to find horizontal asymptotes, and so you can kind of jumble those up as you want. But holes and vertical asymptotes and then domain, definitely your first three in that order. Okay, so we're given the function f of x equals 4x cubed plus 12x squared minus 7x minus 1 divided by 2x cubed plus x squared minus 6x. So I have a third degree polynomial divided by a third degree polynomial. Now, the very first thing that I have to do is I need to factor this. I've got to factor the numerator and I've got to factor the denominator. So that's where we're going to start. So first, we're going to factor our numerator and denominator, because I really can't do much until that's been done. So begin by factoring the numerator. I'm going to break this into multiple steps. So 4x cubed plus 12x squared minus 7x minus 21. So 4 terms, which means I can probably factor by grouping, or at least I hope I can. So from the first 2 terms, I can factor out a 4x squared. That'll leave me with x plus 3. And then from the next 2 terms, factor out a negative 7, leaves me with x plus 3. So now they have the common factor of x plus 3, which can be factored out of both of those, times 4x squared minus 7. Now, you always want to take a look and see, okay, can I factor 4x squared minus 7? You could try to use the quadratic equation. You could try to factor by splitting the middle. This one does not easily factor, so at this point I would be done. Okay, so that's your numerator factored, so I'll rewrite this up here as x plus 3 times 4x squared minus 7. Now I still need to factor the denominator, so let's do that next. So now I'll do the denominator. Okay, denominator is 2x cubed plus x squared minus 6x. And I can factor an x out of each term, so that's where I'm going to start. So this is x times 2x squared plus x minus 6. Now, I can factor 2x squared plus x minus 6. I can choose, and it's entirely up to you as to what you want to do. You can either use the quadratic equation, or you can split the middle, okay, to see if you can factor it. So I'm going to split the middle. If you prefer to use the quadratic equation, then just pause the video, go find your factors, and then come back and see if we get the same answer. So for splitting the middle, I need two numbers that when I multiply them, they equal a times c, and when I add, they equal b. Well, a times c is 2 times negative 6, or negative 12, and b for this problem is 1. So my factors are 4 and negative 3. That's what I'm going to use to split the middle, because 4 minus 3 is 1. 4 times negative 3 is negative 12. So this x just gets drug along for the time being. And so this will be rewritten when I split the middle as 2x squared plus 4x minus 3x minus 6. And then now I have 4 terms, so I can factor by grouping. So I will factor a 2x out of the first 2 terms. That'll leave me with x plus 2. Factor out a negative 3 from the next 2 terms. That's x plus 2. Okay, that now has a common factor of x plus 2 times 2x minus 3. This is fully factored. So that is the factoring of the denominators. The denominator is x times x plus 2 times 2x minus 3. So I haven't solved one single thing yet. All I've done in all of this work is I have factored the numerator and I've factored the denominator, but that has to be step 1. Okay, so now I'm actually ready to start answering some of the questions. So just like I told you, we're going to do the wholes first. So remember, for the wholes, that is where you have a common factor in the numerator and the denominator. So make yourself a note, common factor in numerator and denominator. So when I look at this in factored form, I don't have any common factors in the numerator and the denominator. So what that means is I don't have any wholes. So no wholes. Okay, so over here with wholes, you can either write DNE for does not exist, or you can write none. Either is appropriate, it doesn't matter. Okay, so next I'm going to look at the vertical asymptotes. Now remember, the vertical asymptotes are where the denominator is equal to 0, because we know we can't divide by 0. It's not possible. That's why the graph doesn't exist there. That's why I get that asymptote where the graph doesn't exist. So take the denominator in its factored form. So x times x plus 2 times 2x minus 3. Set it equal to 0, and then find which x values will cause that to be 0. So set each value, each of the x's equal to 0. So x equals 0. X plus 2 equals 0, 2x minus 3 equals 0. So that means x equals 0 is a vertical asymptote, x equals negative 2 is a vertical asymptote, and x equals 3/2 is also a vertical asymptote. So I have 3 vertical asymptotes here. Okay, so I can add that over here. So remember, you always write them as x equals. So x equals 0, x equals negative 2, and x equals 3/2. Okay, now that I have found the wholes and I've found the vertical asymptotes, I know where this graph does not exist. So at this point, it's a logical place to find the domain. So that'll be my next step. I'll find the domain. Okay, the domain, of course, excludes wholes and vertical asymptotes. Okay, so if you want to use a number line, if that makes life easier, then I know that x cannot be negative 2. That's a vertical asymptote. It cannot be 0. Also a vertical asymptote. It cannot be 3/2. If I had a hole, I would add that on here as well, but I don't have any holes. So that means that the domain is negative infinity to negative 2, union negative 2 to 0, union 0 to 3/2, union 3/2 to infinity. Okay, and if you want to add that up here, the right section, that's probably a good idea. So let's rewrite that here. So negative infinity to negative 2, union negative 2 to 0, 0 to 3/2, and 3/2 to infinity. Okay, I think I've got it all. Okay, so there's your domain. And then finally, we want to find our x-intercepts. Now remember, wholes are the common factors. Vertical asymptote is where the denominator equals 0. Then we do the domain. And then step number 4, I'm going to do it over here. I've got a little more room. X-intercepts are where the numerator is equal to 0. Okay, and why is that? Well, that's because if you have 0 in the numerator, 0 divided by anything is 0. And so whatever value it was that you put in to get 0 in the numerator, your output is going to be 0. And so that number, comma 0, is an x-intercept. Okay, and so that's how we get that value. So we're going to take our numerator and set it equal to 0. So my numerator for this problem, back up to the top, is x plus 3 times 4x squared minus 7 equals 0. And that's what I need to solve. Okay, so then I can set each of these factors equal to 0. So that means x plus 3 equals 0, 4x squared minus 7 equals 0. So that means x equal negative 3 is going to be an x-intercept, or negative 3, 0. You always want to write this as a point. And then 4x squared minus 7 equals 0. So to solve, we're going to add 7 to both sides. It'll be 4x squared equals 7. Divide by 4. So that means x squared equals 7/4. Now I need to take the square root of both sides. Be careful here. And so when I take the square root of 7/4, I'm actually taking plus or minus the square root of 7/4. So that means that x will equal plus or minus the square root of 7/4. That's the same as plus or minus the square root of 7 divided by the square root of 4. The square root of 4 is obviously 2. So x is equal to the square root of 7 plus or minus square root of 7 over 2, or x equals the square root of 7/2. I wrote that, so 7/2, and x equals negative the square root of 7/2. Now remember again, x-intercepts are points, so your points are square root of 7/2, comma 0, and negative square root of 7/2, comma 0. Okay, and so those are your x-intercepts. We have 3 of them, negative 3, 0, and plus or minus the square root of 7/2, and 0. So you can add that to your list here at the top. And so your x-intercepts are negative 3, 0, square root of 7/2, and 0, and negative the square root of 7/2, and 0. And that is those are your answers. Okay, and so we were able to find wholes, vertical asymptotes, the domain, and x-intercepts. Okay, so for our next problem, we've got f of x is equal to negative 8x squared plus 26x minus 15 divided by 2x minus 5 squared times x plus 2. So the numerator is a quadratic second-degree polynomial. The denominator, notice, is actually a third-degree polynomial, because if I took 2x minus 5 squared times x plus 2, which is a first-degree polynomial, I would end up with an x cubed. So that's a third-degree polynomial. Okay, so again, our first step is always the same. We need to factor the numerator and the denominator. So I'm going to start by factoring the numerator. Okay, so I've got negative 8x squared plus 26x minus 15. So you can either split the middle or you can use the quadratic equation. It doesn't make any difference, and you can decide. I'm going to split the middle. So a times c, negative 8 times negative 15 is 120, and of course b is 26. So I need two numbers. When I add them, I get 26. When I multiply them, I get 120. Those two numbers are 20 and 6. That's what I'm going to use to split the middle. So negative 8x squared plus 20x plus 6x minus 15. From the first two terms, I'm going to factor out a negative 4x. That'll leave me with 2x minus 5. And then for the next two terms, I will factor out a 3. And that'll leave me with 2x minus 5. So now they both have a common factor of 2x minus 5 times negative 4x plus 3. So there's the factored form of the numerator. So I'm going to rewrite this up here so I can refer back to it. 2x minus 5 times negative 4x plus 3. And then the denominator is already factored. How about that? So I can rewrite that as 2x minus 5. 2x minus 5 squared can be written as 2x minus 5 times 2x minus 5, which might be helpful, times x plus 2. Okay, now first step, like we already talked about before, we're always going to find our wholes first. So the wholes, remember, are the common factors. Okay, I have a common factor of 2x minus 5. So 2x minus 5, I need to determine what the x value is. So set it equal to 0 and solve. Add 5 to both sides. 2x equals 5 divided by 2. So x equals 5 halves is the location of that whole. Now, once I have found the x value for the location of that whole, I'm going to find my simplified version by eliminating those common factors. So I'm going to eliminate 2x minus 5 and 2x minus 5. That will leave me with negative 4x plus 3 in the numerator and 2x minus 5 times x plus 2 in the denominator. That's the simplified version. So we mark this as f sub s of x. That's what I use for everything else going forward. Okay, so now for my whole, to find the y value, using that simplified version, I'm going to substitute in 5 halves. Let me switch back to black. And so that'll be negative 4 times 5 halves plus 3 in the numerator divided by 2 times 5 halves minus 5 times 5 halves plus 2 in the denominator. So negative 4 times 5 halves is negative 20 divided by 2, or negative 10, plus 3 in the numerator divided by 2 times 5 halves. The 2's will cancel, or you can do 2 times 5 is 10, divided by 2 is 5. 5 minus 5 is 0, times 5 halves plus 2. Well, 0 times anything, I don't even have to do the math here, is 0. So I have negative 7 divided by 0. That's a problem. We know we can't divide by 0. So that means this is undefined. Okay, so I have to come back and figure out what's going on here. Why is this undefined? I should have found a y value for this whole, and instead I've got this answer which is undefined. So we're going to come back and figure out, and we're going to look at this a little more closely. So for now, just hang on. Okay, so now we're going to move on and we're going to find our vertical asymptotes. That's always going to be our second step here. So vertical asymptotes are, of course, where the denominator equals 0. Now remember, you're going to use the simplified version of your denominator. So my denominator is 2x minus 5 times x plus 2. So I want to know, where does 2x minus 5 times x plus 2 equal 0? So set each of your factors equal to 0 and solve. So x equals 5 halves. And x equals negative 2. These are my vertical asymptotes. Okay, now we can go back now and we can take a look at what happened with our wholes. Notice something here. If I graph this, okay, I have a vertical asymptote at negative 2. And I have a vertical asymptote at 5 halves, which is the same as 2.5. So this is 2, this is 3. Okay, so here's a vertical asymptote at negative 2, vertical asymptote at 5 halves. Well, notice that our whole was at 5 halves. Well, the reason we couldn't find a y value for the whole is because there's a vertical asymptote there. So everything about that, every point on that vertical asymptote is a whole. It's just a whole string of holes all strung together. Okay, so that's the reason we really don't have a whole. We have a vertical asymptote there. And so anytime you think about it this way, a vertical asymptote trumps a whole, because every point on that line is a whole. So to say that we only have one individual whole in the particular point doesn't really make any sense. Okay, the vertical asymptote makes more sense. So when we're filling in our answers here, what we want to say is our whole does not exist, or none. Okay, either answer is fine. And then you want to include your vertical asymptotes. Your vertical asymptotes are at x equals 5/2 and x equals -2. Now, the reason that this happened, and it's sort of unusual, the reason this happened is because back up at the top, we had 2x minus 5 squared. And so even though we eliminated one of the common factors, we were still left with one of those factors in the denominator, okay? And so that's the reason that that happened. Okay, so from here, we're going to move on. We can go ahead and find the domain because we know that the domain excludes any holes and excludes any vertical asymptotes. So when I'm looking at the domain, it'll be, let's see, -infinity to -2 union -2 to 5/2 union 5/2 to infinity will be my domain. And then finally, the last thing I'm going to find is the x-intercepts. And of course, the x-intercepts are where the numerator is equal to 0. So my numerator is -4x plus 3. So let's see, we'll call this step 3. And so our x-intercepts are where the numerator, which is -4x plus 3, is equal to 0. And we're going to solve for that x value. So subtract 3 from both sides and then divide by -4. And so x is equal to 3/4. Again, x-intercepts are always points. So your value is 3/4, 0. And you can add that to your list above. And so my x-intercepts are at 3/4, 0. Okay, and so those are your final answers. I have no holes because the hole happened to occur in the same place as the vertical asymptote. Vertical asymptote is a bigger deal. Every point on it is a hole. And so my vertical asymptotes are x equals -2, x equals 5/2. Those are going to be the breaks in the domain. And then my x-intercept is at 3/4 and 0. So now we're ready to talk about end behavior and horizontal asymptotes. Now remember, when we talk about end behavior, we're talking about what happens for really, really large values of x, really large positive values of x, really large negative values of x. So what I want to know is as x approaches infinity, where does y go? And as x approaches -infinity, where does y go? Okay, I'm not talking about values between -10 and +10 for x. I'm talking about values for x in the millions or the billions, and values in positive direction or values close to -1,000,000 or -1 billion in the negative direction. Okay, so as it's headed toward infinity, really, really large values, what is y doing? That's what I'm talking about for end behavior. Okay, and the horizontal asymptotes are the values that those graphs are going to track along for those large values of x. Okay, so let f of x equal p of x over d of x be a rational function. Same thing we've talked about the previous 5 pages. And let q of x be the quotient of p of x over d of x. So the quotient just being when I divide the polynomial in the numerator by the polynomial in the denominator, what's that quotient? Okay. Then as x approaches positive or negative infinity, then I know that the values of f of x, or the y values, will model the end behavior of the quotient. Okay, so as x heads to positive or negative infinity, then f of x is going to approach whatever the quotient is, if I were to do the division. Okay, so for the horizontal asymptote, we've got f of x is equal to a polynomial in the numerator divided by a polynomial in the denominator. The polynomial in the numerator in this case is of degree n. So some degree, we're calling it n. And then the polynomial in the denominator is equal to degree m. So here the degree is equal to m. Okay, and so we're going to look at those leading terms, a sub n times x to the n, and then b sub m times x to the m. The leading term of the numerator and the leading term of the denominator, that's what we're going to focus on when we are looking at horizontal asymptotes. We don't really care about the rest, okay? Because remember, we're talking about really large values of x. And so if I have infinity to the 5th degree plus infinity to the 3rd degree plus infinity to the 2nd degree, well, infinity to the 5th degree is so much larger than all the other terms, everything else just becomes negligible. It doesn't make any difference. Okay, so if n is less than m, so what that means is if the degree of the numerator, see if I can fit this on here. So the degree of the numerator is less than the degree of the denominator. Okay, so this is bottom heavy. Degree of the numerator is smaller than the degree of the denominator. It's bottom heavy. Okay, then there's going to be a horizontal asymptote at y equals 0, or at the x-axis. Okay, and so you can sort of think about it like this. If I gave you something like 7x to the 9th degree divided by 2x to the 27th degree. Well, the degree of the numerator is less than the degree of the denominator. If I put in an infinity in for x, I'm going to have infinity to the 9th degree divided by infinity to the 27th degree. Well, infinity to the 27th degree is so much larger. It's unbelievably larger. When you take a number and divide by a much, much larger number, your answer is going to be very, very close to 0. And so that's where we get y equals 0. Okay, so that's my first scenario. Degree of the numerator is less than the degree of the denominator. Second scenario is that the degree of the numerator this time is equal to the degree of the denominator. In that case, then we have a horizontal asymptote at y equals a sub n divided by b sub m. That's those leading coefficients. A sub n is the leading coefficient for the numerator. B sub m is the leading coefficient for the denominator. Okay, so for example, maybe I had 7x to the 5th divided by 2x to the 5th. So now the degree of the numerator is 5, the degree of the denominator is 5. They're obviously equal. So in this case, they cancel each other out. And so what that means is then my horizontal asymptote would be 7 over 2, 7 halves. Okay, and then finally the third scenario is that the degree of the denominator is greater, the degree of the numerator is greater than the degree of the denominator. And in that case, the graph does not have a horizontal asymptote. There is no horizontal asymptote. Okay, so three scenarios here. Either the degree of the numerator is less than the degree of the denominator, in which case y equals 0 is the asymptote, or they're the same. Degree of the numerator is equal to the same degree of the denominator, in which case you look at the leading coefficients. That's the horizontal asymptote. Or if the degree of the numerator is greater, then there is not going to be a horizontal asymptote. Okay, so, and then finally, a rational function may or may not have a horizontal asymptote. Not all of them do. Many do, but not all of them do. Okay, so keep that in mind. Don't feel like you always have to find a horizontal asymptote. All right, so let's work through a couple of examples. So the first one here is that f of x is equal to 2x plus 3 divided by x squared plus 2x minus 3. So I've got a linear equation in the numerator and a quadratic in the denominator. And we're supposed to find the rational functions. So first thing I want to look at is my leading term. Okay, in this one, it's 2x over x squared. So that's my leading term, 2x divided by x squared. Then I'm going to look at the degree of the numerator. Well, the degree of the numerator is understood to be 1. So n is going to equal n is equal to 1. The degree of the denominator is 2. So m is equal to 2. So the degree of the numerator, if we call it n, is less than the degree of the denominator, which is 2, right? 1 is less than 2. And so what that tells me is this one's bottom heavy. Okay, and so when I look at the horizontal asymptote is going to be at y equals 0. Okay, and that is your answer. All right, next one. For the next one, I've got 3x cubed minus 31x minus 18 divided by x cubed plus 3x squared minus x minus 3. So this is a cubic divided by, or a third degree polynomial divided by a third degree polynomial. Again, I'm going to focus on just those leading terms. So the leading term here is 3x cubed divided by x cubed. Now in this scenario, degree of the numerator is 3, the degree of the denominator is also 3. So the degrees are the same. When that happens, then the horizontal asymptote, I look at the leading coefficient, which is 3 for the numerator, and it's understood to be 1 for the denominator. So that, of course, is 3. So that means that my horizontal asymptote is at y equals 3. Now remember, with your horizontal asymptotes, always include y equals. Just like for vertical asymptotes, we always include x equals. Make sure you make yourself a note of that. Okay, and then finally the third one, x cubed minus 3x squared minus 10x plus 13 divided by x squared plus 2x minus 3. So I've got a third degree polynomial divided by a second degree polynomial. So leading term is x cubed divided by x squared. The degree of the numerator is equal to 3. Degree of the denominator is equal to 2. So n is greater than m because, of course, 3 is greater than 2. And what that tells me is there is no horizontal asymptote here, okay? So you would have no horizontal asymptote for this particular graph because what we're doing is we're gathering more information and then eventually we're going to graph all of these with all of this additional information. Okay, so here we are. We're ready to put all of this information together and to graph it. Okay, so I've got the function f of x equals 3x cubed minus 31x minus 18 over x cubed plus 3x squared minus x minus 3. Okay, first thing you have to do is you put it into factored form, which I was nice enough to give you. This is the same function we've been dealing with the previous several pages. Okay, so the takeaway here is when you do this, make sure you do it in an order that makes sense. First thing we're going to find are our holes. From there, we're going to find our vertical asymptotes, then the domain, okay? From there, I would probably find my x-intercepts next and the horizontal asymptotes. And then finally, we haven't talked about the y-intercept, but you know how to find the y-intercept. The y-intercept occurs where x is equal to 0, okay? And so that'll give you one more point that you can graph. I'd love for you to pause here and go through, find all these values and take a shot at the graph and then come back and see how you did. Okay, so most of this information or all of this information except for the y-intercept we had already found on previous pages. So I would find them in this particular order, though I do think that's important. Start with your hole. We found that on page 3. That was -1, 3. Then find your vertical asymptotes. That was x equal 1, x equals -3. From there, you know which values are not in the domain. It's the values of those vertical asymptotes and the hole. So vertical asymptotes and holes are the values that are eliminated from the domain. From there, you can find the x-intercepts. We found those on page 2. Horizontal asymptote we found on page 5. Now, we should talk briefly about the horizontal asymptote. Again, you focus on that leading term, so you can go back to the original function here. In this case, it's 3x cubed over x cubed. The degrees are the same, so that means the horizontal asymptote is whatever the leading coefficients are, 3 over 1, which of course can be simplified to y equals 3. And then the only thing that was new here was the y-intercept. So for the y-intercept, we know that that occurs where x is equal to 0. So using the simplified version of the function, and I suppose I should write the simplified version out here without those common factors, it'll be 3 times x minus 3 times x plus 2 divided by x plus 3 times x minus 1. And so using that version, that simplified version, we will just substitute in 0 for x and you'll get a value of 6. So that means that my y-intercept occurs at 0, 6. Okay, and then plot all of this information in the graph below like I did. At a minimum, you'll have a bunch of points, okay? And then the question is just, well, how do I connect all these points? Starting in the middle, you can see you have a y-intercept at 0, 6 and x-intercept at -2, 0, okay? And then you've got this hole. So if you just start with your x-intercept, come up, jump over your hole, go through your y-intercept, if you continue to go, you know you're going to run up against this vertical asymptote as you move towards x equals 1. And then moving the other direction through the x-intercept, again, you're going to run up against this vertical asymptote at x equals -3. So the middle part of the graph should be relatively easy to graph, okay? And then from there, let's move to the right, because that's that's probably the next easiest section. I know I've got this x-intercept at, let's see, what is this, 3, 0. So if I move through the x-intercept, it's an x-intercept, that's where it crosses the x-axis. As I move along and the x values get larger and larger, I'm going to track along this horizontal asymptote. And then finally moving to the left side of the intercept, I'm going to run up against this vertical asymptote at x equals -1. So then the only portion of the graph I'm left with is the portion that's on the left side of the vertical asymptote at x equals -3. Now we know a couple of different things here. One, we can look at the multiplicity, okay? So Back up to the top in our factored form up here where I found my vertical asymptotes here. If I look at the multiplicity at x plus 3, that multiplicity is 1. Now remember, when the multiplicity is odd, that tells me that the ends are going to go in opposite directions on either side of the vertical asymptote. Okay, so odd multiplicities for both of these. So ends in opposite directions around the asymptote. Okay, and we can see that that's what happened around our asymptote at x equals 1. On the left side, it went to positive infinity, and on the right side, it went to negative infinity, okay? And so around x equals negative 3, we already know it's headed to negative infinity on the right side, so it has to go to positive infinity on the left side, okay? And if that makes you a little bit nervous, you're like, I just don't have a lot of confidence in that, especially on something like a test, plot a point. And that's what I did here at the bottom, as I said, you know what? If I just throw an x value in here, let's see what I get. So I used negative 4, and I got 7. So I know that I have another point on this graph. You can plot as many points as you want on this graph. I have a point at negative 4, 7. And so that gave me a little more confidence to see how this was going to behave. And so you can see that I've got this graph. It's going to go to positive infinity, and then comes through my point that I plotted at negative 4, 7. And then as it comes down, it's going to track again as the x values get very, very large in the negative direction. It's going to go along this horizontal asymptote at y equal 3. Now, important point here. Sometimes you guys give me some crazy stuff on these graphs. Okay, we found all of the x-intercepts. Keep that in mind, okay? The x-intercepts are at negative 2, 0, and at 3, 0. Those are the only x-intercepts on this graph. Sometimes you guys will give me graphs that look like this. They will just snake back and forth across the x-axis. You'll give me a graph that looks something like this. Now keep in mind, I just created 1, 2, 3, 4, 5, 6, 7 additional x-intercepts. And we know that there's only 2 x-intercepts for this problem. They're at 3, 0 and negative 2, 0. So this doesn't make any sense. So be really careful when you do your graphing. Matter of fact, I'm going to erase this because it doesn't make any sense and it's just going to be confusing. So when you're doing your graphing, especially when you get to those more challenging parts of the graph, like we have here on the left side of our vertical asymptote at x equals negative 3, if you need some additional points, then find some additional points. And to do that, you can do that like I did in the box down below here, where I used the simplified version, and I found for x equals negative 4, I got the point negative 4, 7. If you need additional points, you could evaluate at negative 5 or negative 6 or negative 10. And then you'll find that the graph starts to make this shape. And of course, we know as we come down toward the horizontal asymptote that we're going to track right along that horizontal asymptote. So just be careful. You're going to have several parameters that you're going to be using when you do your graphing. You're going to have your x-intercepts. You're going to have your y-intercept. So once you have those, then know that those are the only places that you cross the x and y axis. Don't start snaking back and forth in all of these other spots. So just be careful as you do your graphing. Okay, for page 8, we're going to work backwards. I'm going to give you a graph, and you're going to write the equation of the rational function, okay? So we're going to take each of the pieces and parts, put together what we know. All right, so let's look at this graph and notice some things. I've got a vertical asymptote, I've got a horizontal asymptote, I've got a y-intercept, I've got an x-intercept, okay? And we're going to work from there and see if we can come up with the function for this graph. Okay, so the first thing I notice is, I notice that I've got a x-intercept. So my x-intercept is at x equals 4, okay? So that means that I have a factor of x minus 4, and that will be in the numerator because I know that my x-intercepts are found in the numerator, okay? So as I start to build this function, f of x, I'm going to put x minus 4 in the numerator. Okay, now the next thing I'm going to notice is I've got a vertical asymptote. My vertical asymptote is at x equals 2. Okay, well, x equals 2 means that I have a factor of x minus 2 in the denominator, because that's where I find my vertical asymptotes. So I'm going to put x minus 2 in the denominator. Okay. So I've got this function, x minus 4 divided by x minus 2. I know I've got some leading coefficient. We're going to call it a for the time being, okay? And I know that my horizontal asymptote is at y equals 1. So in order to get a horizontal asymptote of any value other than 0, it'll be 0 if it's bottom heavy. It'll be the leading coefficients if it's top heavy. Sorry, if the degree of the numerator equals the degree of the denominator, okay? And if it's top heavy, there's no horizontal asymptote. So it must be that whatever those leading coefficients, they may have been 1 over 1. It could have been 3 over 3, okay, because that would have simplified to 1. It could have been 4 over 4. That would have simplified to 1. So I don't know what the value is. And so for the time being, I'm just going to call it a, and then we're going to solve for it. And a matter of fact, the way we're going to solve for it is we're going to use the y-intercept, which is at 0, 2. Okay, so that means when x equals 0, the value of this function will be 2. So 2 equals whatever a is, that leading coefficient, times 0 minus 4 divided by 0 minus 2. So 2 equals negative 4a over negative 2, or 2 equals 2a, or 1 equals a. So lo and behold, turns out that that leading coefficient was 1. So that means my final function is f of x equals 1 times x minus 4 divided by x minus 2, or you could simplify that. We don't really usually include the 1. It would be x minus 4 divided by x minus 2. Okay, for this next problem, again, I'm going to start by just building this function. So I've got this, this rational function. We'll call it r of x, just for something different, okay? Looking at the x-intercepts, that's usually where I start. So I can see I have an x-intercept at negative 1, 0, which means I have a factor of x plus 1 in the numerator. So I'm going to add that to the numerator, x plus 1. That's the only x-intercept. I have a whole at 2, 1.5. So there's a whole at x equals 2. So what that tells me is that there's a common factor of x minus 2 in the numerator and in the denominator. I'll add that to my information, x minus 2 over x minus 2. I have a vertical asymptote. Actually, I have two vertical asymptotes, one at x equals negative 2 and one at x equals 1. So what that means is that x plus 2 and x minus 1 are both in the denominator, because that's where, of course, I find vertical asymptotes are in the denominator. So I'll add those, x plus 2 times x minus 1. Anything else? Oh, and then I can see that I have a horizontal asymptote at y equals 0. So what that means is if I'm looking at the degree of the numerator and I'm looking at the degree of the denominator, this one's going to be bottom heavy. Degree of the numerator is going to be less than the degree of the denominator. That's what's going to give me that horizontal asymptote of y equals 0. Okay, and then all I really need now is that leading coefficient. We're going to call it a. Okay, and to find that, I'm going to use the y-intercept. And the y-intercept, of course, is at 0, negative 1. Okay, so I'll solve for that. So negative 1 equals a times 0 plus 1 times 0 minus 2, all divided by 0 minus 2 over 0 plus 2, 0 minus 1. So negative 1 equals a times 1 times negative 2, that'll be negative 2, over negative 2 times positive 2, which is negative 4, times negative 1 is positive 4. So negative 2 over 4, so this is negative 1 equals negative 1/2 a. Multiply both sides by negative 2, okay, and you'll get 2 is equal to a. So that's the final piece of the puzzle that I needed, which means that my rational function r of x is equal to 2 times x plus 1 times x minus 2 over x minus 2 times x plus 2 times x minus 1. And then do a quick sanity check. You can see that you've got those common factors at of x minus 2 and x minus 2, which means x equals 2 is going to be a whole, and I've got that on the graph. I can see if I look at the other factors in the denominator, x plus 2 and x minus 1, that I will get vertical asymptotes at -2 and +1, and I have those. So at -2 and +1, I'd have vertical asymptotes. Mark those. And then finally, in the numerator, x plus 1 tells me I have an x-intercept at -1, 0. And of course I do. And then the final was the horizontal asymptote, which we sort of glazed right over, was that it's y equals 0, which means the degree of the numerator has to be less than the degree of the denominator. Well, if I multiplied together the factors in the numerator, I would have a second degree polynomial in the numerator. I'd have x squared over a third degree polynomial in the denominator, okay, because x times x times x would give me x cubed. I'd have x squared over x cubed. And so obviously the degree of the numerator is less than the degree of the denominator, which of course tells me that y equals 0 is my horizontal asymptote. Okay, so for this function, I'd love for you to pause this, take a shot at this one by yourself, and then come back and see if you see how you did with the answer. Okay, so I guess we'll start to build our function. Again, we'll call it r of x. Okay, first thing I always look for are the x-intercepts. So I have an x-intercept here at 1. I also have a whole at 1, so there's a lot going on at 1. So x-intercept is at x equals 1, which means I have a factor of x minus 1 in the numerator. So x minus 1. I also have a whole at x equals 1. Okay, so that means I have a factor of x minus 1 in the numerator and in the denominator. Okay, so I'm going to have to do x minus 1 again in the numerator and x minus 1 in the denominator. And the reason I know it's written twice is because, remember, if this was written out as the function, we would go through and we would eliminate that whole first. And then from there, I would have to find my x-intercept. So I need the additional x minus 1 in the numerator. Next, I'm going to look at the vertical asymptote. So I have a vertical asymptote at x equals 0 and another one at x equals 2, which means I have a factor of x in the denominator because we don't really write x minus 0, and a factor of x minus 2. So I'll add both of those to the denominator, x and x minus 2. And then finally, there's a horizontal asymptote at y equals 0. Now what that tells me is that the degree of the numerator is less than the degree of the denominator. This one's bottom heavy. Okay, so whatever the degree of the denominator in it is, it has to be more than the degree of the numerator. And then from here, the only other thing I need to solve for is the leading coefficient. We're going to call that a. Okay, so I'm going to have to use some point on the graph, and I usually love to use the y-intercept because it's easy, but I don't have a y-intercept in this graph because I have a vertical asymptote at x equals 0. So there's no y-intercept. So I'm going to have to choose some other point on the graph, okay? And I can choose whichever point that is. I'm going to look for something that crosses nicely just to make life easy. The point that I see that I think I'm going to choose is here. And this point is -1.5 and -0.5. Okay, so -1.5 and -0.5. So not great, but it could be worse. So now I'm going to use those values to solve. So I have -0.5 equals a times -1.5 minus 1 times -1.5 minus 1 divided by -1.5 times -1.5 minus 1 divided by -1.5 minus 2. Thank goodness for a calculator. So -0.5 equals, when you solve all that out, you'll get 6.25a divided by negative 13.125. Definitely use your calculator for this. Multiply both sides by negative 13.125. 0.125, and you will get 1.05. Oh, and then divide by 6.25 after you do that, and you will get 1.05 equals A. Okay, that'll be your final function, and so we will write that as r of x equals 1.05 times x minus 1. We'll write this as x minus 1 squared, because x minus 1 times x minus 1 is x minus 1 squared, over times x minus 1 times x minus 2, and that is your final answer.